I'm Maxim. I'm currently working as a research engineer at a startup called Tessel. So we're doing AI code generation. And before that, over the last 4 years, I worked as a machine learning engineer and then applied scientist at Amazon. And I was lucky enough to be in a position where I worked with infrastructure for large language models, then pre-training them and inference a lot. So I decided maybe I can tell something about this, and if yes, then what? So yeah, I thought maybe about the costs. Maybe I can talk a little bit about the costs. In practice, it won't be really a deep dive talk. I won't give you lots of numbers, nothing seriously tech deep. Just more of a menu, just to understand where the costs are coming from, especially for the big companies where they want to optimize it and why. So yeah, let's dive in. Back to the original question, we're living in the world where everyone is caring about the capabilities, right? Just improving the abilities of your foundational model. So why do we even talk about the costs? Everyone is so focused on making models better at some specific domain, at reasoning, at solving problems, by scaling something like compute, data, model size, anything like this. So why do we talk about the costs when everyone lives in the world where we want just to see the blue line? It turns out companies are caring about this because GPUs are very limited, they're very expensive, and if you, allocate most of them for training one big solution, then you can't, basically do actual research because you just out of the capacity for the GPUs. So you have less flexibility if you're, don't know how to cut the costs. So big tech invests into the cost reduction through making something efficient for GPUs. And my talk will be mostly a menu of themes about where they cut it and how. And the first question which we need to answer is the cost of the experiment. Is it really a problem? The cost which you need to spend to train a model in terms of time, how long does it take, and in terms of money, how much? Is it really a problem? Why it might be important? Because it makes in case the null hypothesis that it costs millions, and bear with me, I'll prove it it affects the decision making for the big companies because they can decide, okay, we don't invest in the experiment at all because it will never pay back. Another reason is because we can understand where to optimize our system, what is the bottleneck and how to improve it. And thirdly, we can allocate more people to work on a specific subject. So cool, it's very simple, right, to understand how much time it takes to train your model. Just express everything in floating point operations. If you express your data and model in number of operations you need to do in terms of computation, then good, you already have numerator, and then you divide it by the speed of your infrastructure, basically how many floating point operations your cloud provider or infra or cluster generates, divide one number for another, and you come up with time to train in seconds. Then you just convert it into a number of millions of GPUs hours you use, and to the cost of 1 hour, and cool, answers to the both questions. So, okay, but how? How do we compute these numbers? That's a question. So let's break it down part by part. Let's start with the numerator, flops for data and model. How many operations we need to do in order to process your data set of P tokens over the model of size n, where n is the number of parameters. Well, people invested into this a lot, and here is a very good paper from OpenAI back in 2021. It's not a coincidence, I think, that Dario Amodei, who is a co-founder and CEO of Anthropic, was a key author of this paper. I think they knew something about the scale. So they wrote a great paper of anatomy of the transformer, exploring how much in depth you need to compute the forward and backward in terms of float point operations for transformer. So what they found out is forward is roughly translates to n, where again n is number of the size of the model for one token, and 2 comes from the fact that you are doing matrix multiplication, so row by column. And backward is much more expensive because you need to, basically twice more expensive as forward because you need to store optimizer states. So it's 4n, and in total it's 6n operations. We neglect all all the other things which don't contribute to this. So 6N just for one token, that's the cost of the flops for your model. If you multiply it by P, which is the data set size, you are good. You're solved the numerator. The hard part is your infrastructure, basically the capacity of the infrastructure and the speed of it. And in order to solve this, you need one more metric called MFU. Nothing serious, it's super simple. Model flops utilization. Basically, it's empirical number. It's ratio of your actual throughput, which you observe in your system, divided by the theoretical number reported by the provider. For example, NVIDIA always reports their theoretical numbers on the page for each GPU. The question is like how to get right? You need to estimate you need to benchmark your system, and it might be very dependent on the case, because when you're training a model, you are parallelizing it, you are sharding it across the GPUs, and that what affects the MFU as well. So tensor parallelism degree plays a big role, and in practice you really need to benchmark it. So if you're a small company and you're owning just hundreds of GPUs, it's easy to benchmark it. But it turns out that in practice, when you're going to scale to thousands of GPUs, everything starts to saturate between 30 to 50%. And there are a lot of benchmarks from different companies, from Meta, for example, in their Llama 3 report. They generously showed what their numbers were. So when they train it with 16K GPUs, the best they could in terms of utilizations of the whole system is just like 38% of the maximum flops the system could provide. And they also empirically show that with more nodes in the cluster, the efficiency drops down, which is obvious. The question is like, how do you push it like as close as possible to 50%? So yeah, if you're a big company, then you don't need to benchmark anything. You can just use the numbers on that scale, just grab them from the papers, and that's it. That's good enough. Cool. Now we have all the variables in our solution, and we can compute the time to train your model in seconds. Just plug it in, divide one number after another. Let's do a case study. Let's estimate how much it will take to train a real llama for 105B. It's not a coincidence that I took this model specifically, because in the paper they report how many days it took. So let's estimate the accuracy of our proposed benchmark. We know that Llama 3, the biggest one, was 405 billion parameters. It was trained with 15.6 trillion tokens. Cool. Just plug into our equation, and we have the flops for data and model. We know that the largest model was trained with 16K GPUs. Amazing. Just plug in this into the equation about the flops infra, divide one number on another, we get 70 days. More than 2 months just to train one model on 16 H100 GPUs. And then if you convert it roughly to the cost, like the H100 GPU on the Amazon AWS costs $2 per hour. In practice, of course, it will be cheaper for Meta because they own their own cluster. But if you just compute how expensive it is, it turns out it's just like a cost of one experiment of one model, 52 millions, and it doesn't take into account the people, the fact that you need to do multiple runs and so on. So it's crazy how expensive this is, and if you want to train a model, just think twice. Maybe you don't need it. The hot takeaways from this is that every optimization matters, because if you can cut any of the part, like speed up any piece of the equation, then you get dramatic improvements, either over the speed of the time or in the cost. Secondly, back-of-the-envelope calculations is the base for any big companies. Before investing in some experiment, just do a lot of arithmetic, a lot of simple calculations. And third, there is a big demand on the market in big companies for hiring people who know how to do it, who know how to optimize the system, basically performance engineers, CUDA kernel engineers, specialists in distributed training. Cool, that's the first theme. And the second, more practical, let's go closer to the models. It's about long context window for the models. So it's a very interesting application, right? If you are having a long context window, you can just upload all your books, all your documents, and then query your model through the API. You don't need to maintain any RAG pipelines. You can simplify everything. So that's the benefit for you as a customer, but for the company as well, because if you have a very long context window, like millions or like billions of tokens, infinite context window, then you don't need to make lots of, maintain lots of inference calls. The infrastructure simplifies. And yeah, it also simplifies the memory management. You need to care less about how to, evict the context window and so on. And also it's a differentiator feature on the market. Everyone wants to have a large context window. If implemented very accurately, like optimized, and also if it brings any accuracy improvements, because it turns out one context window doesn't work very well. To highlight even more why big companies are interested in long context is, I'm giving an example of startup. Basically, there are lots of the startups who are focusing just on this, on finding an approach how to extend the context window. And big companies are super interested not to do it themselves, but to invest a huge amount of money just in the startups, just to hire, have more people working on this topic. And okay, there's someone on the background. So here is an example of a magic dev startup. They raised 515 million in less than 2 years on the market without any product from Google and other funds just to work on this topic. They had a pretty good demo of having a model with 100 million tokens context window, but nothing beyond that. And yeah, what is the reality? Where we are in terms of really the context window. So being more, there is a recent paper from NVIDIA about actually trying now to make a long context window into the existing model. So they propose a recipe where they take a pre-trained model. In their experiments, it was Llama 8B. They train it in 2 stages. First stage is here for extending the context window. They extended it from 128K tokens to 4 million. They do it by creating an in-house data set of very long documents, and then they also scale their open embeddings and fine-tune it in SFT. And then they do the second stage, where they return the reasoning and instruction tuning capabilities into the model through, again, regular SFT, but now on the high-quality data. And they show that the metrics of the new model remains the same across the instruction-oriented benchmarks, so baseline capabilities are not affected at all. And they show that on the long context-specific benchmarks, everything goes up. But the only interesting one is Infinite Bench. It's a data set of multi-hop question answering, where a model really needs to focus on a very long context and do a multi-turns over the document. And it improves from 24.16 to 32.49, but yeah, just a little bit. Again, nothing really super impressive, and that's why this problem is still unsolved, and there is no good solution. Everyone wants to find something, wants to find an efficient way, a compressed way, but nothing works really well. So that's why it's also an interesting topic for the research. Try new methods, try new recipes, and so on. And it can be also optimized in various ways, either through new model architecture or through better infrastructure or through both. So it's interesting topic for the research. And now we're moving to the final, on our menu, final topic, the reasoning. Reasoning is nowadays everywhere. It's a core capability of every big model. It's a default in AI code generation, where you're typing in your cursor or in Claude Code. It has reasoning. The reasoning improves the capabilities of any daily usage of the model. So whenever you're using ChatGPT, for example, with O4 Mini, it thinks a little bit. And it also allows to solve really hard problems. Like recently, Google Gemini model solved and won the International Olympiads in mathematics. So it can do a lot of really complicated things. And many companies are interested in cutting the costs of the reasoning. Can we produce less tokens, but at the same time be as efficient as with very verbose amount of tokens? And here it's just like options how to do it. One is to be very smart about this, in the sense that let's make it hybrid and let's allow the user to decide how many tokens the model will generate. So it's up to the user to set up the the number of maximum tokens to generate explicitly, but it doesn't solve the problem directly, because for some requests, the thinking still might require lots of tokens, and super hard problems require a lot of reasoning. So it doesn't solve the problem again directly. Only on average you can optimize the cost a bit. The second option is to train smaller models, and that's a very interesting, in my opinion, domain. For example, there is a picture from the Microsoft paper where they trained Phi4 model reasoner. They distilled it from a very large reasoner on the trails of a very big model into just a 14B model, and they showed it can be very competitive on specific domains, especially where there is a clear verification against proprietary models, but still, like, the gap is big, and also there are lots of challenges to train. The model collapses all the time, and all the intuition about how reward modeling works for big models doesn't keep for small models. So interesting topic, but not a big success. Third option, which I initially wanted to dedicate the full theme just about this, is speculative decoding. How many people are familiar with speculative decoding? Okay, not that many. So I will just outline the idea of this method. Is that assume you have like two models, one small model and one big model. Both are reasoners, and the small model, it's cheap to inference it. So imagine let's run just this small model to generate n tokens. It does it autoregressively, but because it's small, it will be faster. And then you put this n tokens into the large model, which is verifier model, and it doesn't generate them. It just validates whether they are true, whether they are like aligned or not. If they are, then we just accept them, and we don't need to regenerate. We just continue with the next token. So we're cutting the costs by putting a lot of effort into the small model, and the big model is there to just verify and discard sometimes. So the method starts to work really great when you somehow introduce a smart criteria into how to sample the tokens. The default methods in a speculative decoding doesn't work very well. It doesn't take into account the contextual appropriateness of the tokens and discards a lot of them. That's why the acceptance rate is very small. But with methods like judge decode, which I used on my own, you can get a lot of boost from this method. Fourth option, like why do we keep with transformers? Let's throw away transformers and just go with a different approach. Let's use diffusion models. Diffusion models are very popular in computer vision, so the idea is that you generate the picture iteratively. Let's say you start from noise, then you remove a noise a little bit, and you go to second iteration. But the thing is, like, you generated the whole picture in one go, and why not to apply the same idea to text? It's unclear how. It's quite complex, but imagine you can do it. Then you generate the whole text in one call, and then every iteration just adjust the text a little bit, still making everything working very fast. And Gemini, again from DeepMind, they shared that they work on this. They allow they don't allow to use this model publicly. You can only join the waitlist, but they show huge improvements, saying that they can achieve 1,479 tokens per second on the GPU, which is like huge comparing to 200, 300 on average for current solutions. So it's like a big boost. But that's not it. There is another option. Let's forget about the models at all and just use a new hardware. Let's use better chips. Let's replace GPUs with something faster. And here it's Cerberus, a startup which works on the chips specifically. And this screenshot was added just recently, like today, literally. The last column, OpenAI model, which was dropped yesterday, they already benchmarked it on the Cerberus, and they show 3,000 tokens per second, just like, yeah, very a lot, comparing to the 200 on the GPU. How it works, again, like it's NDA, but the idea is that they have a new chip with trillions of transistors on the chip rather than billions on the standard GPU chip. And that's it. That's all for me. So takeaways from the talk, that there are a lot of areas where you can invest in order to improve not just capabilities of the models, but making them cheaper as well. Again, a lot of these domains and areas are driven by the demand and cost because companies want to see paybacks now, not in a year. They want to improve and see some benefits right now. And that's why a lot of these problems are very specific to the big tech because that amount of scale, that amount of the compute is only available there. And it's a good news because more hiring, they need more people to do this. But the skill set changed a little bit. Now they don't need classical software engineers, they need more specialists, more people involved about the performance optimization, about the distributed training and so on. And that's it. Thank you for attendance. Thank you for listening to me. Let's stay connected. Here's my LinkedIn, my Telegram channel where I talk about ML research, pretty much the same things as here. And yeah, if you have questions, if I have time, I'll be happy to answer. Thank you.